AI coding agents routinely solve complex logic problems in isolated local environments. Yet, when deployed as automated workers in real engineering pipelines, these agents collapse. The cause of this failure lies in the default execution cycle of most agents, the react loop. In this pattern, an LLM reasons about a problem, requests a tool, receives a result, and responds. This default loop operates entirely in the present tense. It possesses no structural memory of its own operational state outside its immediate context window. If an external API drops a connection or a single tool returns an unhandled string format, that context state breaks. The execution halts instantly and silently, leaving the repository in an inconsistent or half-finished state. High scores on coding benchmarks offer little value if the surrounding execution environment cannot survive a standard network timeout. The Open-SWE architecture offers a concrete case study in solving this fragility. It demonstrates transitioning a model from a brittle script into a durable engineering service. This transition involves shifting engineering resources away from prompt optimization and toward the design of a deterministic control plane. To function at scale, an automated system must enforce three strict boundaries: closure over entry to control how tasks begin, closure over action to restrict tool use, and closure over lifecycle to ensure tasks finish visibly. Achieving this reliability requires moving complexity out of the prompt and into the surrounding engineering infrastructure. A live production environment is chaotic. Development tasks arrive asynchronously from GitHub webhooks, Slack threads, and dashboard API calls, all carrying different payload formats. To achieve closure over entry, the control plane intercepts every request, normalizing incoming data into a deterministic thread context before triggering the model. The system then routes that thread to initialize stream resumability and checkpoint continuity. This yields a critical operational advantage. When a long operation hits a token limit or experiences a network error, the job does not fail. The dispatcher retrieves the thread identity, reconnects the state, and resumes execution seamlessly from the saved checkpoint. A durable run tied to a deterministic thread provides a highly effective reliability lever for long-horizon agent operations. Moving past the entry layer brings us to the React core itself. While libraries like Deep Agents manage this cycle, exposing a raw reasoning loop to a codebase remains a severe operational hazard. Open-SWE isolates the model by encasing every reasoning and tool turn inside a strict middleware stack. When models receive unexpected tool outputs, they repeatedly request the same failing tool, entering recursive loops that consume massive token budgets. The model call limit middleware backs as hard cap, tracking recursion depth, intercepting runaway behavior, and stopping the process with a failure notification. Simultaneously, the model call timeout middleware enforces a strict time budget per worker action, ensuring that an unresponsive sandbox environment cannot hang the process indefinitely. The architecture also protects against premature termination through the ensure no empty message protocol. If the model attempts to exit while work signals remain, this middleware injects a continuation instruction, preventing dead loops that masquerade as natural task completions. These constraints form a first-class safety architecture executed at runtime to prevent silent failures. A common operational error involves building a universally capable agent by providing a library of dozens of different execution tools to a single prompt. High tool counts generate prompt entropy. Role confusion leads the model to execute a destructive write command when only reading a file was required. Open-SWE solves this by fragmenting the monolithic prompt. It divides responsibilities into multiple separate graphs, specifically the main agent, reviewer, and analyzer pipelines. Each graph gets a strict capability envelope, its toolset pruned based on its specific role. The reviewer graph operates on a strictly read-only envelope, restricted to gathering evidence. Only the main agent graph possesses the tools required to execute commands or write data. Decomposing graphs and isolating tools by role provides a more stable security model than attempting to instruct a single prompt not to modify the repository. Notably, Open-SWE does not place a heavy general-purpose verifier inside the main coding loop to double-check every step. Embedding continuous evaluation stalls execution speed. Therefore, the harness pushes strict verification outward, relying on asynchronous operational workflows. The primary mechanism for this is the CI monitor graph, which functions as a first-class operational correction loop. When a task finishes and triggers a test failure in continuous integration, the CI monitor observes the failure state and autonomously dispatches a bounded, fix-aware retry run, keeping the remediation process automated. Autonomous operations rely on these external remediation paths to bridge the gap between a failed run and a successful deployment. The harness dictates the logic and the limits of the agent's behavior, but it does not run the code. It delegates terminal commands to a physical execution sandbox. This creates the architecture's final critical vulnerability, the provider and sandbox trust boundary. If the deployment infrastructure configures the external sandbox with overly broad permissions, the model gains capabilities that exceed the graph's intended design. A permissive execution environment allows the agent to trigger system-level effects that completely bypass the middleware safety spine. In modern agent architecture, infrastructure and deployment hardening have become as critical to safety as the code review process itself. Reviewing the Open-SWE blueprint reveals 3 mandates for production harness design. First, wrapping executions in durable runs and deterministic thread contexts provides a highly effective reliability lever for long coding operations. Second, enforcing role-specific graph boundaries prevents errors more effectively than refining the tool schemas inside a single prompt. Third, the unresolved frontier of agent engineering requires establishing hard operational policies directly on sandbox execution boundaries. Scaling an AI agent from ephemeral script to durable infrastructure is a success of operational orchestration. In a production environment, the harness scaffolding provides the operational security that the model's reasoning alone cannot guarantee.